Okay, so I'm supposed to give you a tutorial on random matrix theory. So when Chandan asked me, I promptly said yes. though I was not very sure about... firstly, I have not worked on random matrix theory for a very, very long time. And also, the things I know may not be very useful to the people in the audience. But anyway, I have tried to put together some lecture. So let me begin by a quote from Freeman Dyson, who is a pioneer in this subject. I mean, he's a great physicist. So there's a long remark in one of his papers. So let me just say that about random matrix theory, a new kind of statistical mechanics in which we renounce exact knowledge of the system itself. That's what we want to do. And he was, of course, talking in the context of complex nuclei. So we picture a complex nucleus. And I would actually like to substitute nucleus by complex system as a black box in which a large number of particles are interacting according to unknown laws. I think that is the point, according to unknown laws. The problem is then to define in a mathematically precise way an ensemble of systems in which all possible laws of interaction are equally probable. I think this is a pretty deep and weighty statement. I don't think I understand a lot of it, but when somebody says he doesn't understand the system, yet he can calculate something, it's perhaps because of something like this. All right, so there's something cut out in this slide. Can you make this slide smaller? Let's just begin by saying that at least we understand what we are talking about here, that you have large nuclei. At least this is a quote from many decades ago. And the random matrix is essentially the matrix elements of the unknown Hamiltonian, and it's distributed according to this simple probability law to begin with. Now, there are many, many applications of this subject. Trace M square. Number. There are many applications, and some of them I understand, some of them I've just been popularly reading about. The spectra of chaotic systems. This is a very important and open application, very important application of random matrix theory, basically because of the fact that, as you know, the spectrum, the eigenvalues of the random matrix have a repulsive character. Then there are very important applications to statistical properties of S matrices in quantum transport. There is this famous Kumar-Mello equation. It's an old friend of mine, Kumar. Then there are applications to number theory. And these are very fascinating things about the distribution of the zeros of this Riemann zeta function. It's very statistical. There's a lot of work in this direction. Then random surfaces and two-dimensional quantum gravity used to be a very active area a couple of decades ago. And then there is a lot of work in, you want to solve gauge theories, so you invent model gauge theories which are of simple random matrices and try to learn from them. Then there is statistics, there is free probability theory, about which I know very little, but perhaps somebody here can explain in a future tutorial. There are applications to engineering and statistics of critical points in landscape. For example, there the random matrix is a Hessian. Okay, so these are, a large number of applications. And what I will do now is do something very simple. I will explain to you or derive in various ways Wigner's semicircle law, its generalizations, and how we can generalize this type of ideas to multiple random matrices which are non-commuting, which is a very hard problem, but I will come to that later on. So let's begin with the simplest problem. This is a partition function, and this is some measure of random Hermitian matrices. I will simply focus in this talk mostly on Hermitian matrices. And this action has one very important property, and it is the fact that it is invariant under transforming this Hermitian matrix by a unitary transformation, okay? So this is a very fundamental point. Now, what is this measure? The space of Hermitian matrices is actually a pretty featureless space. It's a flat space. And it's the metric on this space is simply defined in terms of the infinitesimal matrices dm and dm dagger, as I have defined over here. And now we want to go to a polar decomposition, which means that I parameterize this Hermitian matrix in terms of its eigenvalues, this diagonal matrix, and this unitary matrix, okay? And I compute dm, and it's not very difficult. The dm is just d of d, that is the diagonal matrix, plus this important commutator of this pullback form. So this pullback form I will call polar coordinates, and I'll explain in a minute why this is something you're very familiar with. And then you compute this in terms of components, put it all together in this line element, which is defined essentially in terms of these components and the sum over I and j, and you get this following important formula. So now this is basically a change of variables from the space of flat Hermitian matrices to invariants, okay, like the eigenvalues and the unitary matrices. And so you can compute now the Jacobian of this transformation, and it turns out to be this very famous factor. And this very famous factor essentially says that if the eigenvalues coincide, then the measure vanishes. And where have you seen that? Not only the measure vanishes, but the dimension of this space shrinks by 3. You've seen this when you go in ordinary Euclidean space to polar coordinates. And this object over here is nothing but the analog in 3 dimensions of r square. Okay, r squared dr. Okay, and this determinant actually, this can be written as a Van der Waals determinant, a property which I will not use in this talk, but it's actually of fundamental importance in the exact calculation of this type of partition functions, which was done by many people later on. Okay, so here we are. So this measure, I'm going to divide out by the volume of the unitary group because the action is invariant under the transformations of the unitary group. And I essentially land up with a statistical mechanics problem like this. Okay. Now, can I ask, I mean, is everybody with me, or, I mean, I'm sure everybody knows this. This is sort of, oh, Jacobian. So if you, yeah, okay. So suppose you have some coordinate system, okay? Let's say x, y, z. And suppose you want to go to polar coordinates. So the polar coordinates are functions of x, y, z. Then you want to find a volume, dx, dy, dz, in terms of dr, d theta, and d phi. So you have a Jacobian there, which is r square, and it vanishes at r equal to 0. That's the exact analog of this. I mean, there's absolutely no difference in the concept over here. So please be free to ask me all these questions. Yes.
How about DR?
Yes, so you can also work with real symmetric matrices, and you can carry out a similar program. The only difference will be that this measure factor over here, this 2 will not be there. The Jacobian is slightly different. Okay. All right. So you can have a very complicated action which has multi-trace operators, but we will restrict ourselves to begin with the action which Wigner worked. That is just the quadratic m square. All right, So here you have this problem, a very simple problem. This is a quadratic potential over here, okay? So if this term was not there, the repulsion was not there between the eigenvalues, all of them will settle down basically at the origin. And it's not an interesting system. However, what happens is that because of this repulsion, these eigenvalues, n of them sort of spread out along the real line, but they can't really go to infinity because there's a competition from this attractive potential. Okay, so this is the physics picture, that they will settle down in some section of the real line, which is to be determined. And there will be a density of these eigenvalues if they are very, very finely distributed. Means if n is very large and they are very close by, you can approximate the distribution in terms of a continuous function. And you arrive at determining that distribution by basically saying that the variational derivative of the action is 0. Or this is the force balance condition basically. That the force due to the harmonic potential or any potential that is there is balanced basically by the collective Coulomb repulsion. Okay. Now let's do one trick. This trick is the following. Take 1 upon lambda I minus z. At the moment z is a real number. Multiply it, this equation, and sum both sides. And introduce a certain kernel, which is a fundamental object in this subject. In mathematical literature, it's called the Stieltjes kernel, but it's just some analytic function that you want to work with eventually when Z is complex. Okay, so this is a object like this, and it's like a propagator. So, and you look at its Laplace transform. People who are particle physicists working in string theory are usually interested in this object, actually, which is called a loop operator. I will not go into it unless you ask me questions at the end, but it has to do with string theory and gauge theories. But this is an important operator anyway. And now you realize that this entire equation can be rewritten in terms of a single differential equation. It's a single derivative differential equation, and given the function f of z is related to the potential in this way. Quite amazing, right? So for large n, you can actually ignore this term, and what you get essentially is an algebraic equation. So with every matrix model is associated an algebraic curve. And here there are lots of very interesting connections with algebraic geometry and taking the large n amounts to neglecting this term. So it becomes an algebraic equation. N, oh, I'm sorry. N is the dimension of the Hermitian matrix. It was there on the first side. Yeah, thanks. The number of eigenvalues is n, capital N, and n goes to infinity. Okay, so you have this algebraic equation, and it's a curve. Loudly, Nivedita. Where did I get it from? Oh, I did it in front of you. Here, behold. This is the equation, and you can rewrite this equation in terms of this function, right? This spectral function. Okay. Just, it's algebra. Just algebra. Believe me. I am sure you have done it, and I'll come to it. It's what you have done, maybe you've forgotten. Okay, all right. Okay, so this is one way of looking at this problem. And
I had a question.
Yes.
So is there a physics intuition for introducing that additional z, and is it like the location of a test charge? Is it probing the system?
Yes, I think so, because if you look at, I have rewritten this equation in terms of, I redefined this object, y of z, but it is precisely the force on a single eigenvalue. If you look at this equation over here, if you just keep one eigenvalue in this term, then that's just the force term, right? The total force was 0 when you took all the eigenvalues together. But now I just look at one, and this is the force actually. So this part of the talk is actually taken from a very beautiful paper by Kamran Wafa and Robert Drygraf on matrix models, Calabi-Yau spaces, geometry, and stuff like that. Okay, but I'll give you the references later on. Yes. Extent of randomness is just given by the action, right? I mean, the probability distribution.
Typically there's some kind of scale associated with that, like in a Gaussian. Is there any fundamental scale here?
I'm not following the question actually.
Like the variance of the Gaussian, for example.
Yeah, oh, I see, okay. The variance of the Gaussian, that's what you meant, okay.
Yes.
Set to 1. Thank you. Yeah, that's right, yeah. Right, that's right, thanks. Okay, so I hope everybody is with me. Then, of course, I know how to solve this algebraic equation, okay? And it's just a quadratic equation which you can solve. Now, this is an analytic function, W of Z, because it's an analytic function in the complex plane minus the real line. And I have to look for solutions which have this boundary condition, because it was 1 upon m minus z trace, right? So for large z, the eigenvalues being bounded, you'll essentially get this boundary condition. And that sort of eliminates the minus sign over here. And this is the function. This is the solution of the full problem. And once I know this function, and I know its connection with the eigenvalue density, which is just over here, just take this, write in terms of eigenvalues, introduce the density variable, density of eigenvalues, and when they are very closely spaced, this is a continuous function, and this is a very well-known formula. So once you have this formula, and you know this analytic function, then you can compute the rho of lambda by essentially the discontinuity theorem, and it's just, this is the Wigner semicircle law, basically. And the eigenvalues are just distributed on this segment of the real line, and they are continuous, and here is the famous Wigner semicircle law. Okay, it goes to 0 very sharply. Now, just one comment, and this comment is important over here, so that someday you can go and think about it. But these eigenvalues that we are talking about in the n equal to infinity limit are sort of frozen. Okay. Now, once you make n finite and talk of fluctuations, then these fluctuations actually start unfreezing the eigenvalues in at these two edges. And the way you do this smoothing by adding certain operators to the matrix model depends on which type of relevant operator you add, and you get a whole host of multi-critical matrix models, essentially by trying to smoothen out this type of singularity over here. I know that it may be difficult to follow what I just said, but this just for the record, in case you are interested, this is a huge subject actually in matrix theory. Okay, a few comments over here. Now, we did this problem for a quadratic trace m square action, but you can work with an arbitrary W of lambda, and one can solve the this analytic function in the cut plane. Now, if you have, for example, a potential like this, some eigenvalues may settle down here, some others settle down here. So you have a multi-cut problem actually, and you have a more sophisticated solution. And yeah, there are many ramifications of this which I don't want to go into, but I just wanted to say that there can be a very, very interesting mathematical problem of reconstructing this function from its values at these branch cuts. Okay, All right. So second comment is that I did not work with, as yet, with multi-trace operators. So these are single trace operators, trace of m squared, trace of m fourth, trace of m to any power, integer power. But I didn't talk as yet about these guys, that is trace, squares of traces and higher powers over here, which appear in all types of applications, at least in the work I do. This type of things appear all the time. And I think it also appears in the very interesting work on this landscape, where the Hessian is the random matrix. This is work of Dean and Bray, which I'm familiar with, and Majumdar and others. I think Surya Ganguly is going to talk about perhaps this type of things. Perhaps. Okay. Oh great. Thanks. Okay, so this, the way to solve this type of problem is basically, in the large n limit, you can replace this multi-trace operator in terms of single traces, and then redo everything as we discussed before, and self-consistently determine this trace m square. Okay. Now, this way I showed you of how to solve this type of problem is not a traditional way of doing it, because the traditional way of doing it looks at this type of integral equation and introduces this analytic function, which defines what is called a Riemann-Hilbert problem. And I am saying all this because I've seen a lot of literature actually which uses this type of method to solve these problems. And once again, you can obtain the eigenvalue distribution from the discontinuity across this cut. Okay, now I just wanted to mention something which you don't find written in many of the applications that one is familiar with, but recently Satya Majumdar has been emphasizing the importance of what I'm just going to talk to you about as something which is very important to understand large deviation theory, random matrices, and going beyond Tracy-Widom and stuff like that. What is this point? Point is that let us look at what the solution space is for a random unitary matrix. Okay, so unitary matrix is much more complicated because it has this, it's a nonlinear space to begin with, unlike the space of Hermitian matrices. And once again, you define this distribution of eigenvalues. And there's a coupling constant over here, okay? And you can make a very interesting analogy of, charged particles on a circle interacting by some simple potential. This gives you a cosine potential, a periodic potential, and they are repelling each other actually, just like before. Now, if the electric field, this coupling constant can be interpreted as the electric field in this direction, is of a certain value between 0 and 1, the charges are sort of distributed uniformly or distributed all around a circle. Okay, so this is the distribution. So at E equal to 0, of course, the distribution is uniform. As you increase E, the distribution tends to thin out over here and settle over here. What happens at E equal to 1 is that there's a gap in the spectrum that opens up, and there's a new solution actually of this equation. Now this you can see very clearly if you work with this Riemann-Hilbert method, and you can solve this problem exactly. So this might be an interesting example of a phase transition in a random matrix problem. And this phase transition is very useful in some areas in statistical mechanics and also in string theory and related areas. So incidentally, I come from string theory area, so that's why the tone of the talk is slanted towards that. I cannot help that actually. Okay, all right. So the last thing I want to say here is that one of the important reasons why people looked at random matrix theory, that it has some universal properties, universal local properties of the spectrum. I'm not going to do anything about it except state it, okay? So you would like to know about the separation of this eigenvalue spectrum, okay? And what I have written down is called a Wigner surmise. And this is an ongoing subject, and there is a very recent paper I saw, which I couldn't understand very well, but by Terence Tao, trying to give a very solid background to these equations. So I've just written down 3 formula for the probability of as a function of S, where S is defined as this level spacing, and for the Hermitian matrices, which I've been talking about, and also for the symmetric matrices, the real symmetric matrices, and the quaternionic matrices. These are the formulae. And one very important point is all of them vanish at S equal to 0. So this is the sort of thing that the spectrum essentially is very repulsive, actually. It doesn't have any symmetry. And so the spectrum is repulsive. And therefore, random matrices are very ideal to model complex chaotic systems. I do know very well one example of recent times in which this has played an important role, and this is what is called the SYK model in condensed matter physics. SYK means Sachdev E. Kitaev, and that model exhibits amazing complex properties, including scrambling and chaos. And there are studies actually which model the SYK model in terms of random matrices, and which are very successful in a certain range of couplings and indicate this type of behavior. Okay, the last comment is references. I didn't have any time to do it, but in the submitted PDF, which will appear finally, you will get them. All right. So now let me turn to something which I think is very fundamental to this whole subject, whichever way you talk about it, in terms of free probability or in terms of Schwinger-Dyson equations, and it is this point of factorization at large n. Okay. So here is the issue. So we saw that in the one matrix model, it is very easy to compute all these correlations, any number of them, just by a single function of the eigenvalue distribution. And in fact, you can very easily see that there is no fluctuation in this object. The fluctuations are all down by 1 upon n square. And this idea actually led to the interesting concept of what is called a master field. This, I think, is due to Ed Witten a long time ago, and also Migdal, that this must be a very generic property of any theory at large n, however complicated, even a gauge theory, that certain types of operators show no fluctuation. They are simply classical. And one of the big goals actually in at least my subject of particle physics is how do you solve a gauge theory at large n? This was a big dream in the early 70s. It has not worked out, but on the way we have learned a hell of a lot actually. So, all right, so let me just give you a certain flavor of what this is. So now the question is the following: how do you deal with a matrix problem, let's say of matrices M1 and M2, in which M1 and M2 do not commute? So the question is it possible to formulate the large n limit of an arbitrary complicated matrix theory or a string field theory or whatever actually? And the examples are multi-matrix models or non-abelian gauge theories, and these are very complicated objects, but can you write down in principle a set of equations, which you may not be able to solve, but characterizes the whole system at large n? This is the mean field theory of matrix theory. Okay, so let me let me give you, I want to show you the following thing, that in matrix theories, or in any quantum field theory, which has matrix degrees of freedom, there is something called a topological expansion. And this was discovered in the 1970s by 't Hooft. And it's the following. Let us look at this very simple type of model, okay? There's no quantum field theory, nothing actually. These are just constant matrices. M square, M cube, M fourth, whatever. Now, a typical way of trying to analyze this problem would be to do perturbation theory. Perturbation theory in which the Gaussian is the dominant term, and then these are like interactions. So you do what is called Wick's theorem in quantum field theory. And you do Feynman diagrams of this type of integral, which means basically that you look at the Gaussian propagator. The Gaussian propagator you designate by this very important double line notation, okay? And these are Hermitian matrices, these are ordered lines. It's like some sort of a color that is flowing through these lines. And these are color indices. Then you can diagrammatically represent a cubic interaction this way, and a quartic interaction this way, etc., okay? And then you start forming Feynman diagrams. So I've just written down one simple vacuum diagram over here. This is a cubic vertex, and these are these propagators. And in general, there is an expansion in terms of Feynman diagrams of this object. So let us notice something very important over here. So if you look at this diagram, there are 4 3-point vertices. 1, 2, 3, 4. Okay? There are 6 propagators. And there are 4 index loops. By an index loop, I mean a closed line like this, where the indices have to be summed. So every time you sum something, you get a factor of n. So you just look at this counting, okay? And compute this object, f minus e plus v. And for this diagram, it turns out to be 2. So this diagram goes as n square, that is this number, times some power of the coupling constant, which is not terribly important. What is terribly important is that this object actually is the Euler character of the sphere. And so this diagram actually can be wrapped onto a sphere, okay? I cannot go in many more details about the higher genus, but let me just say the following, that in general, in any matrix theory, with any number of matrices, okay, however complicated in any number of dimensions, this expansion is true in perturbation theory. Take any graph, and that graph has the following characteristics. It has so many propagators. So each propagator brings a lambda upon n, right? Because of the way it is situated over here, the propagator gives the inverse, lambda upon n, and the vertices give n upon lambda, each one of them. So you can add this up. So many propagators, so many vertices, and so many faces. And lo and behold, every time you do this, every time, you get n to the power of a topological invariant. That's the Euler character, okay? So this means basically that these graphs have one-to-one correspondence with 2-dimensional manifolds of various topologies. Sphere with a handle, sphere with 2 handles, so and so. So you can organize the large n expansion as a topological expansion. And this was done by 't Hooft. It's one of the big steps in this subject. And I just thought I'd mention it to you, that the partition functions log, that's the free energy, can be actually written in terms of this object. This is just a side remark. Now, what I want to tell you basically is that because of the topological expansion in perturbation theory, it is possible to establish factorization of operators, of products of complicated operators in perturbation theory. I'll give a very simple example to you that let us look at the partition function with this most simple action, okay? Just the propagator. And let's compute trace m4 times trace m4. We know how to compute in terms of the distribution of eigenvalues, but let's do something else. So I start writing down Feynman diagrams, okay? The first Feynman diagram I'll write down is a disconnected diagram. So you see I took this 4-point vertex and I just stitched it with these propagators. And this is the dominant contribution, this factored object. It has 4 propagators, 6 index loops, and therefore this object goes as n square. Now let's look at what is called a connected diagram. Connected diagram means I can't cut this diagram anywhere and it will fall apart. Okay? That's not true over here. If you do this computation again, there are 4 propagators, 4 index loops, and you get n to the power of 0. So this is subdominant compared to this. This tells you that the factorized object actually is more dominant than the connected diagrams. And so this is, I mean, I've shown it to you in a very simple example that this is true, that there is no fluctuation in trace m to the 4th because of this property. But this is true for anything. It's true for a very complicated gauge theory which has an infinite number of matrices. There's no problem. This is true. That's the point I wanted to make in a very simple way. So the topological expansion in perturbation theory enables us to say that there are certain operators in the theory which show no fluctuation at large n. Okay. Is everybody with me, or you have some questions I can... Sorry? Yes, but anybody can ask any question actually. So, yeah. I'm around here. Yeah. Yeah. I'm around here. I mean, my family will not be very happy, but I'm around here. Okay. Or am I going too fast? Or I think people are not very familiar with Feynman diagrams, perturbation theory. Yes. Okay. Yeah. I'll do that actually. Okay. Yeah. So what I'm doing actually, let me explain a little bit to you. Is the following: that I have something like this, right? Now, let me. So we have trace m square. Let me just put some coupling constants here. Simple. This is small. So what I do is, basically I want to compute, therefore, e to the minus trace m square. This is the Gaussian term. This is what all of quantum field theory does. The Gaussian term is the dominant term. And then you expand this guy, e to the this, so it's 1 plus g trace m cube plus g square trace m cube square, etc. Okay. So now I want to compute these guys. This is just Gaussian integrals, right? And I compute them using a diagrammatic expansion, actually, which was invented by Feynman. I mean, just to do this type of Gaussian integrals with lots of interactions. So this is why in electrodynamics, if you talk about the scattering of 2 electrons, and they exchange a certain photon, and then there can be corrections to this. So what is the Gaussian theory around which I'm doing all this? It's the free Maxwell theory, plus the free Dirac equation. No interactions. So that's the 0th order part. And everything else I want to expand. And people, and combinatorically, this is rather complicated actually. So people develop diagrams to do this type of thing. This is what I meant by Feynman diagrams. And the great insight of 't Hooft was that he introduced for a simple propagator of this matrix a so-called double line notation, in which these indices just go around. For example, I have something like this. This index I is just going to flow in this. And therefore, I get this contribution. Things like that. So Feynman diagrams are a very efficient way of doing perturbation theory. And you can take care of a lot of combinatoric factors actually, which are they're a pain basically, but you get to it. Okay. So this was just my 2 minute on Feynman diagrams. Yes. Sorry. Okay, so this is, okay, so Wick's theorem is basically, how do I say it? Basically doing Gaussian integrals, right? I don't know what else to say. Would you, I mean, anybody is free to explain. All right, so now this is the last part of the talk. So what do you do when you have more than one matrix or a whole theory in which the matrices are not commuting with each other? What do you do? And one way which we found is very useful is what is called the method of the Schwinger-Dyson equations. There is equations for Green's functions or word identities for Green's functions. If you combine it with this factorization I talked about, then you can write down closed sets of equations for a large class of operators which don't fluctuate. That is what I want to just give you a certain flavor of. So this is the statement of the Schwinger-Dyson equation. It's a triviality actually, basically. You take a total derivative, you put in this matrix, and that depends on a lot of intuition that you have about what to expect. And this is exponential of minus the action, and this is obviously 0 because this is a flat space, so its total derivative is 0. Then you learn how to do this simple type of calculations of the nth power of this matrix. Essentially can be written this way. So there is a very interesting thing that happens, that you have k of them multiplied, then there's a cut. And then there is this n minus 1 minus k of them. So this is, all this intuition to do this type of thing came from string theory actually. You want string splitting. Okay, you want string splitting. So how do you do this type of things? So this is a very simple splitting that you encounter in a very simple model like this. And then you use this, and I'll leave it as an exercise to you that this immediately reproduces this equation that you sort of, we started with doing our, in terms of eigenvalues, So I didn't do no eigenvalue problem. No eigenvalues, nothing. And just factorization at large n, that these are operators which are classical and don't fluctuate, and you arrive at this algebraic equation. So this is known. It's a simple thing. Now let me tell you what is known but much more difficult. And this is a very interesting work actually, which was done by Nivedita here, Sanjay Jain and Sriram Shastri many years ago. Just wanted to give you a flavor of how do you work when you have a two matrix problem and those matrices don't commute. Well, how do you do it actually? So this is it. This is exact solution. So it's very beautiful. So firstly, you got to figure out the class of operators actually which will form a closed set of equations. It's not terribly difficult, but you can do that. And these people did this. So these are the sort of kernels that they looked at. this one, which is natural. Then you have this correlator over here, the connected part, okay? Then you have this one with a B sticking over here, and you have this one with an A sticking over here. And this is a product of the trace, actually. So this is the object, actually, which is of physical relevance, and you can now find a closed set of equations, actually, for all these guys. And this is the exact answer at large N. I think it's quite remarkable that you can do things like that, which are of actual practical interest. And I think these authors had the Calogero-Sutherland model in mind and some properties of chaos. But anyway, this is how the two-matrix model can be actually solved. So let me just end with some comments now. That the Schwinger-Dyson equations plus factorization imply exact equations, for example, for Wilson loops in a non-abelian lattice case theory. So this is something which comes out. And then, in fact, most of this, preceded the work on random matrices, at least in our community. People are interested always in gauge theories, how to solve gauge theories. So how to write down equations for Wilson loops and how the Wilson loops split, etc. So you have a closed set of exact equations for the Wilson loop, but very hard to solve, but maybe someday somebody can solve them. Then, for example, in models with vector degrees of freedom, like spins or fermions, you can form bilocal variables. These are invariant variables, and n is very large, and n usually is of the order of the size of the system or bigger. Then you have another random matrix. You can form these bilocal variables, and believe me, this technique was used to solve exactly the Simons theory at large N with matter fields. For people in condensed matter, they'll appreciate this. Actually, this is not a trivial problem to solve, but it could be solved this way. And also the Sachdev-Ikitayev model in the large N limit could be solved this way, actually, using this type of random matrices. So this is more or less what I had prepared, actually, to tell you. And I'd be very happy to take questions, and I think there's time. I didn't know exactly what more to prepare because it would get more and more technical. So if you have any questions, please ask me. I may not know the answers to most of them, but it's okay. Yeah. Yes. Yes. I'll tell you what I mean exactly. I'll tell you. Take any operator, any observable, any object, square it, okay? And then take this guy. Okay. 0. Am I right? Basically, what I'm saying is that minus, this is the basic statement. Sorry? Okay. This is true. Yes, right. Yeah, it's the n. 1 upon n sets the scale of what is small. Yes. Exactly. Exactly. It is very much like if you take a system in quantum mechanics, you have quantum fluctuations, right, which are controlled by h bar, right, Planck's constant. So if you start taking that to 0, you will recover classical mechanics, right? It's exactly that. What is the classical mechanics of this complicated large N systems is the question that at least we are very interested in. Yeah. Solve the so-called O3 sigma model. It's a model of spins, right? You have, let's say, This is related to the problem of the ferromagnet, right? I mean, these are spins at some point x, right? And they are sort of, coupled like you want to do this type of problem, right? That's your physical interest. Fortunately, this model, over many years, people were able to make progress in using Bethe ansatz and those type of ideas. But at large n, when the number of spins grows very large, you can solve the model in 2 minutes. And you essentially capture all the physical ideas of this problem at n equal to 3. Not below that, but at n equal to 3. So I think it is just a way of trying to give an analytical handle on complicated problems, right?
How does that equation feed into your action derivation, like the fluctuation or the lack of fluctuation?
Oh, how does that? Oh, I see. So I said is the following here. You see, just look at this very simple example, okay? I did not spell out all the steps, but you can compute this, okay? So this is some algebraic formula, right? I mean, that algebraic formula, there occurs an expectation value like this, which makes it very difficult to solve this problem. But if you use this factorization, which you can prove at least in perturbation theory, this object, that's the same as this. Then you can solve the problem. That's what I was saying. In this case, you can do much, much, much more. You can solve the full large and everything you can do. All the corrections you can compute, but not in all problems you can do that actually, right? You are asking me, I'm very tempted to say something. I'm going to say it anyway. How do you make sense of the large n limit, or for very complicated systems, at least the ones that people work in quantum field theory and gauge theories? So this is this gauge gravity duality. There is something called the ADS-CFT correspondence, which I'm sure everybody has heard about. I don't know. I'm okay. Okay. So I'll tell you what it is actually. So this large n limit essentially is trying to calculate some sort of a mean field. No. See, what did we do in this eigenvalue problem? We computed the mean field in which all the eigenvalues are living, right? And we found a solution for that mean field in terms of this eigenvalue density. So the job is basically to find a mean field always. Now, somebody made a amazing conjecture actually, very supported. I mean, this is perhaps even deeper than the Riemann hypothesis, I think. That lot of quantum field theories at large n, the mean field actually lives in a dimension 1 higher than the system. And that system is a theory of gravity, which evaluates the correlations of this large n theory. So this is an astounding statement. Most of us are making a living out of such things, but it's about 20 years old now. And 20th anniversary of this is being celebrated, including at ICTS in May. So this is the big thing, actually, that the mean field does not live in the space-time you're working in, but in one higher dimension, and is given by some configuration of the solution of Einstein's equations. So I thought it's a good idea to know about this. I mean, this is one of the most highly cited papers, at least in our subject. This is due to Juan Maldacena, actually, this ADS-CFT correspondence. So that's what it is. I don't know, maybe these ideas may have some help, because you can do computations, actually, by just solving Einstein equations in many computations. May not be totally realistic, but you get some idea of what these systems are.
Learning, because there are these that ADS-CFT is actually becoming relevant to deep learning because there's toy versions of it using these quantum tensor networks and so on. And now people are writing papers about the relationship between deep learning and quantum tensor networks and so on. So I'm not sure if those papers are deep or just a very simple isomorphism. But anyway, these are percolating in the air at the moment. It's kind of interesting.
Thank you. So it was not a very irrelevant comment I made. Yes. Yeah. Not in the spin glass phase, because that's what Kitaev did. He killed that spin glass phase, actually. Yes. Right. So maybe I should write down what is the SYK model. Okay. So SYK model is a model of basically Majorana fermions. It means basically gamma matrices, all interacting by means of some Hamiltonian, which is IJKL and psi I, psi j, psi k, psi l, IJKL. And this is a random coupling, actually. This is your model. So if you add, for example, a term like this, then there will be a phase transition. But this model in the large n limit reproduces many properties of black holes. So it's a random spin type of model, which Kitaev showed has fantastic properties, actually, that in the limit of large n and strong coupling, this model has a hidden symmetry, which in fact there's a new infrared fixed point, which is described by a conformally invariant theory. But very importantly, the full theory is divergent at that point. So you got to go a little bit away from that fixed point, and then you can sort of solve this problem. And this is the problem which exhibits quantum chaos. This one. So if you compute, let's say, some 4-point correlation, which approximately something like this. So see, what happens basically is that the strong coupling limit of this theory is described in terms of certain low energy modes, which are coming from the reparameterization invariance of this model. And these low energy modes, they are basically like pseudo Goldstone modes. You can compute essentially this function, and you can compute and calculate real-time growth like this, which is so this is the Lyapunov exponent, saturated Lyapunov exponent for this model. So it is a model that exhibits, model of random system that exhibits the saturation of the chaos bound. And this is then modeled by random matrix theory, by a whole set of people, and they find agreements and stuff like that. So it's all completely connected, actually, yeah. And why is this interesting? Because black holes are the most efficient scramblers. They always satisfy the chaos bound. Yeah. I'm sorry, I think I'm looking at Partha and Chandan and thinking there are only physicists here, and I'm just talking. I'm so sorry. Please ask me some other questions. Yeah. Yeah. Sure. Yeah. Sure. Initial few slides, right? This one? Which one? All right. Yes. Right. So here it is, this line element is written in terms of the Hermitian matrices and now written in terms of eigenvalues and these angles. So it's a polar decomposition. And then you compute the Jacobian of this. So if you have a if you have a map like this, X set of variables going into some set of other variables which are functions of the x's. Exactly. This matrix is the one I'm calculating, the determinant of this. Yeah. Okay. Next slide is this. Yes. So all you now do is you integrate over the eigenvalues, which are invariant under unitary transformations. They are like the radial coordinates, but with a Jacobian like this. This is the repulsive measure over here. And then I take this measure and put it up in the exponent, actually. Then it looks like a physics problem, And then I minimize this action, and I find for you the distribution of the eigenvalues and the spacings and all types of things you can do once you do this map. This one? That is because this is the first term, actually. That's the Wx. So it's x squared. It's a quadratic thing. So you can have x cube, x4, whatever, and this will be reflected in this term. So for example, I gave you this example, right? In which it's not x squared, but something which has a quartic term also, right? Then how do you solve this type of problem? Same way. Now the eigenvalues will be sitting a little bit here and a little bit here. And so the math problem is a multi-cut problem. And sort of multi-trace operators. So these ones actually. Yeah. Well, this one? Right. Here it is. See, what I did is basically I introduced an analytic function. This describes a certain curve in the complex plane. Okay. So you can imagine matrix models are just large and limit maps into whole set of curves in the complex plane, algebraic curves. And from those curves, you can pull out your information about the density of eigenvalues depending on the analytic structure. So this is the simplest one I did for you, in which the Wigner problem has a 1 here. Other problems have other polynomials, actually.
This you got by limiting.
Yeah, what I did was I sent n to infinity, so I got rid of the derivative. So I don't have a differential equation, I have an algebraic equation. So maybe I thought I'd do it this way because this is not done usually in standard random matrix theory reviews and all that. So yeah, but this is a very powerful method of doing it. Very powerful. Yes. It is a Coulomb gas problem, right? 1D, absolutely right. No, that's absolutely correct. This was Dyson had. Anybody could have guessed that, but Dyson used it very effectively later on, actually. Sure. This one. Oh. So I think originally this model is due to Sachdev and Yee. Chandan can answer this question. I mean, he knows all this very well. To model spin glass problems. Sorry?
Sold antipathically in this model.
This model, yes. But you can actually devise a SYK model which is like this, in which the fermion is slightly different properties, different low energy modes, etc., corresponding to this U1 charge. Yes.
Okay.
No. So the planar ones are the ones which are most dominant. Then there are diagrams which, for example, I'll draw a diagram like this, like this. This diagram. This diagram cannot be fitted on a sphere. It can be fitted on a torus. And so on, actually. So there is a very beautiful connection between Feynman diagrams with matrix degrees of freedom and the topology of Riemann surfaces. And having said all this, let me just say something more, actually, that suppose you take some sort of set of Feynman diagrams which are like this, like this, like this, like this, maybe somewhere else, etc. Then you can talk about some sort of a dual space over here in which you put points over here. And you can join these points like this. And you can prove actually that if you take any diagram of a matrix type of theory on a Riemann surface, then you can understand a triangulation, a discretization of the Riemann surface. And this is the reason why matrix models are important for fluctuating membrane problems. Yeah. And then fluctuating membrane in 2 dimensions is a quantum gravity problem. So, yeah. Yes.
Yeah. When mathematicians derive an equation for the resolvent, the little w that you have there,
yes,
they use a cavity type method where they take the n by n matrix, get rid of 1 row and 1 column to get an n minus 1 matrix, n by n minus 1 matrix, and then they write down a self-consistent equation for the resolvent of the n by n in terms of the n minus 1, and then in large limit you get an algebraic equation. Is there a relationship between that cavity method and this method? I mean, they yield the same answer, but is there some deeper connection?
Yeah, so I gave you 2 derivations of this. One is the Schwinger-Dyson and the other one is this. No, I don't know actually. You thin out the matrix basically, slowly, and find a recursion relation. Yeah, I gave an example at the very end. I gave an example of a fairly difficult problem. Yeah, this one. Yeah. So there are. So you can still write down a closed set of equations, and I mean. Wouldn't do what I did, but there's a whole connection of multi-matrix models with the theory of integrable systems, which was developed by mathematicians and by Mike Douglas and all these people. There are amazing things people do with multi-matrix models. But generically, I don't know. Generically, like a gauge theory is a multi-matrix model, which is generically hard. Yeah. Yes, so long time ago, I mean, people discussed what is called this Eguchi-Kawai reduction, actually, that you can take the large n limit. What you do is that you represent a translation group in the unitary matrix. And so you can take all the degrees of freedom and transport them to a unit cube or something. And you have a very complicated model, spin glass type model, actually. You have to then do quenching in order to reproduce the standard Feynman diagrams of large end limit. So people have done that, but and then they do that, then they numerically simulate those models, and reasonably good. But yeah, so what is large end limit good for? It's good for gravity. Maybe. Yes, yeah, absolutely. The other way around, right. Will you quantize it?
So has there been an attempt to classify surfaces in the way that you have shown this topological expansion? So for example, something that distinguishes a torus from a sphere. So, I mean, if you go both way around, then you end up the same place, but that still doesn't tell you that it's a sphere. So
all I said was a certain diagram can be fitted. Like you have some codes and
now
on something.
So now the other way around. So is there a generic way of characterizing surfaces using these diagrams?
Yes, that's what I'm saying. So the sum over all surfaces can essentially be written as a matrix model. That's the point I was trying to make. Yeah. We are nearing our end. Okay. Well, I hope it got across. Thank you. We even talked of ADS-CFT and tensor networks. And
my hope is that you wait a few years and there'll be surprising connections.
Yes.
We'll hear more about it.
Right.
Just like in condensed matter physics.
Yeah. But all the time I feel it's a one-way street. I want to get something out of the other communities and what they do, explain, do something like that. And maybe we can learn something there. Yeah. Thanks.